Welcome to the Creating Parameterized and Recursive Types lesson. Today we'll learn about parameterizing types, both how to create and how to use parameterized type synonyms and data types. Then we will use that knowledge to create 3 different recursive data types. And finally, we will learn about kinds and the newType keyword. Let's get started. A value constructor takes values as parameters and produces a value. A type constructor takes types as parameters and produces a type. We can use type constructors with both type synonyms and newTypes. Let's start with type synonyms. Going back to our last type synonym, we have this. 3 synonyms: the name, that is the same as string, the address, that is a tuple of 2 values, a pair with a string and int, and the person type, that is a pair of name and address. Imagine that after using it for a while, we find out that we also have to identify companies by their numeric ID and providers by the alphanumeric ID. We could do something like this. In this case, we added 4 new type synonyms: the company ID, that is an integer, the provider ID, that is a string, the company, that is a tuple of company ID and address, and provider, that is a tuple of provider ID and address. We get our desired result, but at the expense of repeating the same structure 3 times: person, company, and provider, or tuples with something and an address. A different approach will be to define a parametric type synonym. For example, we could create the entity A type synonym. To define a parametric type synonym, we have to indicate the parameter to the left of the equal sign and use it to the right, same as with functions. And now, every time we use entity A, we can adjust the type of A according to our needs. For example, this time we add in just 3 more type synonyms: the company ID, that is an int, the provider ID, that is a string, and the entity A type synonym, that is a tuple of A's and addresses. And below we have 4 different values with 4 different types. The first value is of type entity name, and it contains a name in the first value of the tuple. The second is of type entity company ID, and it contains a company ID in the first. The third is an entity provider ID with an provider ID. And finally, we can use other types. For example, this is the entity bool type, that it contains a boolean as a first value, and so on and so forth. Notice that entity by itself is a type constructor, not a type. So no value can have a type of just entity. And also, entity name, entity company ID, entity provider, and so on and so forth are completely different types, and the compiler will treat them as that. Those are 2 important details that you will have to remember. We can also use multiple parameters. For example, the address type synonym is also a pair, but one that doesn't have address as the second element of the pair. So we could generalize entity even more and convert the 2 values of the pair into parameterized types, like this. As you can see, now entity takes 2 parameters, A and B, and generates a tuple of type A and B. And now address is a synonym to a specific case of entity where the first parameter is a string and the second is an int. And because of that, now every time we use entity for the previous value, we have to pass the address type synonym to have a complete type. Of course, now the name entity doesn't make much sense, and our types are starting to get a bit convoluted. I just wanted to show you that you could use more than one type parameter. It's not a big deal. But that's pretty much it for type synonyms. They are useful to provide extra context when needed, and they provide certain flexibility, allowing for type parameters. But other than that, they are pretty boring. Let's learn the good stuff. You know what I mean. Let's learn about parameterizing data types. To add type parameters while defining new types, you do the same with functions and parameterized type synonyms. You add the parameter to the left of the equal sign and optionally use it to the right. Here we are defining a brand new type, a type that represents a box that contains values. In this case, box is a type constructor that takes one type variable, a. So we could have values of type box bool, box char, box float, etc. And we have two type constructors, empty and has. Checking their type, we see that empty is of type box A and has is of type A to box A. Okay, so we see this for all A in the two types. I told you, I think we saw this previously, and I told you to ignore it. You can still ignore it. And this for all is something that is implicitly on all polymorphic types. And it just means that for all types A, this rule applies. And for all types A, this rule applies. But this doesn't change anything about your type or how it works. So you could just ignore everything until the dot and just read the type as we always did. If you want to learn more about this is called universal quantifier, and when you use certain extensions of Haskell, it can be useful. But for now, it doesn't add to the understanding of the code. So empty is for when the box is empty. In this case, empty is of type box A, meaning it's polymorphic. We don't know the type of what's inside because it's empty. And the has value constructor will be dependent of the type of the value that we will pass to the constructor. So the type of has is box and the type of the object that it contains. For example, we can create box1 that has this string inside. So the type of box1 is box of list of characters. And we also have box2 that it's empty, and because it doesn't have anything, we still have the box A type. And we can not only create values, but we can also modify and combine the value of the boxes. For example, let's create the function add n that takes a value of type A that is constrained to be an instance of the type class num, and a box A where A is also constrained to be an instance of the num type class, because for this A applies to all the A's inside the signature. And we will get also a box A as a result. So the first parameter is the value that we want to add, and the second parameter is the box that contains the value that we want to be added to the new one. So in the data definition, we see that we have two constructors. This means that usually you need two definitions to take into account all the cases. So the first case is when the box is empty. In the case that the box is empty, you could return a has with the number that we pass inside. But that will work same as having a box that has 0 and a number, because it will be the same as having has 0 here. I choose for it to work differently, and I return an empty box. And in the case that the box does have something, I pattern match to extract the A and add the A to the number and wrap it again with the has constructor. So if we add 3 to the box has 1, we get has 4 as a result. Another thing that we could do is to add the values of 2 different boxes. This is pretty much the same as we did before, but in this case, we take 2 boxes as input and return a single box. And in the case that the second is empty, return empty. In the case that the first is empty, I just ignore the second and return empty. And we have left just the case when both boxes have something. So we pattern match the first one to extract A, we pattern match the second one to extract B, we add A plus B and wrap it again to get a type box A. If we apply the function add boxes to has3 and has7, we get has10. And if we apply add boxes function to has5 and empty, we get empty back. So we can create a bunch of operations around our new type. But what if we want to extract the value inside the box? The case of the has a value constructor is easy. We just need to pattern match and return an A. But what about the case when the box is empty? Well, we could ask for a default value to return if the box is empty. That way, we always return a value. So if we translate this into code, we get this. The extract function takes a value of type A without any constraint because we are not really operating on the value. So it can be any type. And it takes also a value of type box A and returns a value of type A. In the case that the box is empty, we take the default value and return it. In the case that the box has some value, we return the value and ignore the default. And here we have a bunch of examples of how it works. We could keep creating more functions for box A, but there's still a lot to cover, so let's keep going. We can also use type constructors with record syntax. Imagine we also want the option of using other ways of representing colors in our shape. Previously, we used string values and wrote down the color's name. But other situations could warrant different formats, like hexadecimal or RGB values. So it's better if we parameterize our type like this. Now, shape takes a type parameter A, and our color field can be of any type A. So our shape can be of type shape of string, shape of int, etc. For example, we can create circle S that takes a circle and the color is a string. So this value is of type shape list of chars. And we can create a type synonym RGB that has a tuple of 3 values int. Usually RGB is represented using integers from 0 to 255, 1 for red, 1 for green, 1 for blue. So we create this type synonym to make it easier to read RGB instead of this tuple of 3 elements. And we create a value using the circle constructor, but in this case, instead of passing a list of characters, we pass the 3 values inside a tuple and indicate that is of type RGB. So circle RGB is of type shape RGB. And all the other properties of record types still apply. Now that we know all these ways of creating types, we'll go through a few more examples to hone in on the knowledge. But because we are highly efficient students, we will kill two birds with one stone and learn about recursive data types while at it. We can use type synonyms inside other type synonyms, but for technical reasons, we cannot define recursive type synonyms. We can, though, define recursive data types. Here's the situation. Elon Musk wants to rebuild Twitter using Haskell, and you're interviewing for the position. The first question is to define a data type for a tweet. A tweet has its contents, the number of retweets, the likes, the comments, the metadata, etc. That will be a huge data type. But the interviewer doesn't care about the details. He wants you to present the general idea. So you provide this. The data type tweet with just one constructor with 3 fields. You used record syntax because you know this type will eventually contain many more fields, and it will be cumbersome to use regular syntax. You also figure out that a comment to a tweet is just another tweet. So you can recursively use the type list of tweets as the type of the comments inside the tweet data type. As you can see, the tweets data constructor takes a string, the contents, an int, the likes, and a list of tweets, the comments, and returns a tweet. And to test it out, you create a realistic tweet value. In this case, we define the value tweet of type tweet that has a tweet inside with the contents of the tweet, the likes of the tweet, and the list of comments inside that tweet. Each comment is another tweet. The first one has its body, like, and list of comments, and the second the same, except that the second also has one tweet as a comment. The interviewer liked your idea, but was skeptical about how easy it will be to work with a type like this. And to prove that it's super easy, you wrote a function to measure the engagement based on the number of likes and responses the tweets and all the tweets that tweet generated had. And this function looks like this. We have the engagement function that takes a tweet and returns an integer. And to implement it, we only pattern match for the fields that it needed, the likes and the comments. Then it added the likes and the amount of comments of that tweet. And to that, it added the sum of numbers generated by recursively mapping the engagement function we are defining right now to all the tweets in the list of comments. And if we apply the engagement function to our previous tweet, we see that it correctly returns 13 because it goes to the first tweet, adds 5 likes plus the 2 tweets it generated, and then it recursively takes the tweets inside the list of comments and adds 0 likes and 0 comments, plus 2 likes and 1 comment, plus the 3 likes of the final comment, adding up to 13. The interviewer is so impressed that she stops the interview short and offers you a senior position. But you reject the offer when you found out that now salaries of all Twitter's employees are paid in Dogecoin. So you move to the next adventure. After successfully completing Twitter's interview process and rejecting their offer, your confidence is skyrocketing, and you decide to give it a go at Google. The initial interviews are okay, but it's time for the real deal, the technical interview. You show up on time, and so does the interviewer. We are up for a good start. And here comes the first question. Write a data type that represents a linear sequence of nodes where each node contains a value and points to the rest of the sequence. Easy enough. So you need a data type similar to the box we created before, because the empty constructor represents an empty node, and the has constructor is a node that has a value inside. The problem is that you need to contain a sequence of these boxes. Luckily, you know you can pass multiple parameters to a value constructor. So you can simply add another box as the second parameter of the has constructor, like this. That new parameter means that the has value constructor now contains a value and a box that can contain another value and a box that can contain another value, and so on and so forth. And with that, boom, we have a data type that is a linear sequence of boxes where each box has a value and points to the rest of the boxes. And that's awesome. But you did all this in your head, and the interviewer started to get worried about your long silence. So you explained the reasoning, but changed the word box with sequence and a has with node, because that's the language of the question. So you presented the final solution like this. That data type represents a sequence of nodes that could be either empty or have a node that contains a value and points to the rest of the sequence. It's the same type as before, but changing the names makes you think differently about what's happening. And to prove that it works as expected, you create a few values. We have the sequence1 value that is of type sequence A, because it's an empty sequence, so we don't know which type is the value that it will contain if it had any values. We also have sequence 2 that is of type sequence char that contains a node with a value that points to another node that it's empty. We have sequence 3 of type sequence bool that has 3 nodes. A node that contains true and points to the rest of the sequence that starts with a second node that contains false and points to the rest of the sequence that is just an empty node, and so on and so forth. Right after that, the interviewer looked at you dead in the eye and asked, "And how is this useful?" You hesitated for a second. And that's when you vaguely remember a Haskell course you did a long time ago. Yes, video lectures can be recursive too. You smile and say, "Oh, I'll tell you how useful this is," and proceed to slightly modify the data type to make a point. This is what you did. Since value constructors are just functions, you can also create infix value constructors, with the caveat that they have to start with a colon. In this case, you define this weird arrow value constructor that takes the node's value as its first argument and the rest of the sequence as a second argument. So it works the same as the node constructor, but now is an infix constructor. So the previous sequence 4, our last sequence we defined, now looks like this. The weird arrow constructor takes the value of the first node as its first argument and the rest of the sequence as its second argument. Then the first node of that sequence contains the value 2 and points to the rest of the sequence, so on and so forth. So it's a sequence of 3 nodes plus an empty node. Looks familiar? Exactly. That's a list. If we compare the two side by side, it's pretty obvious. Instead of the sequence integer type, we have list of integer type. This is just another way of writing list of integer. And instead of the weird arrow constructor, we have the cons constructor. And instead of the empty sequence, we have the empty list. And if we compare our type with how lists are defined in the actual Haskell source code, we see this. They are virtually the same type, but lists have some special extra sugary syntax to make them easier to use. And that's why you chose the fixity of the weird arrow constructor to be infix right 5, because that's the fixity of the cons operator. After presenting that evidence, the utility of the type is obvious. You just recreated the list type, and lists are everywhere. The interviewer was pleased, but he was just starting, and he asked, "Now write a function to check if a specific element is inside this sequence." No problem, you had to implement the lm function for your new type the same way it's already implemented for list. So we define it like this. You define the lm sequence function that takes a value of type A and a value of type sequence A and returns a boolean, where A is an instance of the equality type class. Because you will be checking for equality, you need to check if the value A is inside this sequence. You have two constructors, so you start with two equations, one for the empty sequence constructor and one for the weird arrow constructor. If the sequence is empty, you don't care about the other value because you know it won't be inside an empty node, so you return false. And if the sequence has at least one non-empty node, you pattern match to extract the value of the first node of the sequence and check if that node is equal to the value provided. And then recursively apply the lmseq function to the same initial value and the rest of the sequence. If at least one element of the list is equal to the value provided, you want to return true. So you use the OR operator that takes two booleans and returns true if either one is true. That way, as soon as you get one match, you will get true till the end. And you will know that the value is inside this sequence. Using this function, we can check if an element is inside our sequence like this. We have sequence 5 that contains 5 nodes, 4 with values and 1 empty. And we can apply this lmSequence function to check if the value C is inside the sequence. We see that it returns false. And to check if the percentage value is inside the sequence, and we'll see that it returns true because it's right here. Well done, says the interviewer. But I have a problem with this. I have tens of thousands of elements. And if we have to check one by one in sequence, it will take forever. You saw this coming from a mile away and said, no problem. If we have the values ordered, we could use a binary search tree. The interviewer was right. Imagine you have 10,000 items to go through. If you go one by one, it will take forever. So what do? Think about the last time you looked for a word in the dictionary. No, not on the computer. I mean an actual physical dictionary. How did you do it? Did you go to the first page, look for the word there, and then the second page, and so on and so forth? No. you straight up opened the dictionary in the middle. And when you saw that the word wasn't there, you chose one of the halves based on the order of the alphabet, split that half in half, and check for the word again. That way, every time you check, you reduce the size of the problem in half. That's called a binary search algorithm, and it's much better than linear search we used before. How much better, you ask? For example, if the dictionary has 10,000 pages, when searching linearly, the worst case scenario, meaning the word is at the very end, will be to check all 10,000 pages. But if we use the binary search algorithm, the worst case scenario will be that we need to check 13 pages. 13, that's it. You can see how this is a game changer for efficiency. So, we want to create a data structure that allows us to easily search that way. There are a few we could use, but one of the most famous ones is the binary search tree, also called sorted binary tree. And it looks like this. In a binary tree, each node can have at most 2 child nodes. It has only one root, that is a node without a parent, node 8 in this case, and has only one path to get to any node. So, the node of value 3 is the child of the node 8, that is the root, and the parent of the node 1 and 6. And the only way to get to node 7 is through 8, 3, 6, 7. There's only one route to get to that node and any other node. That's a binary tree. Now, what makes this binary tree a binary search tree is that the value of each node is greater than all the values under the node's left subtree and smaller than the ones under its right subtree. For example, all the values under the node 8's left subtree are smaller than 8. And all the values under the node 8 right subtree are bigger than 8. Again, all the values under the node 3 left subtree are smaller than 3, and all the values under the node 3 right subtree are bigger than 3. By knowing this, each time we check the value of a node, and it's not the one we're looking for, we know that if the value is smaller, we have to keep looking on the left subtree. And if the value is bigger, we have to keep looking on the right subtree, allowing us to discard all the nodes of the other branch and reducing the size of the problem in half. Same as we did with the dictionary example. Okay, so how do we translate this to code? Well, Haskell makes it surprisingly easier. In our sequence type, we have one case when the node was empty and one where the node had a value and pointed to the rest of the sequence. To make a binary search tree, we need virtually the same type, except that now we want the node to point up to 2 different sequences that are now trees. So the data type we need is this one. We have the tree data type that can be either empty or have a node that contains a value and points to both the left subtree and the right subtree. And that's it. The only difference lies in the node constructor, which now contains a value and 2 different subtrees. Now, let's plant a few trees. We could create a value called, for example, empty tree of type tree that has just an empty tree, a 1-level tree, in this case of type tree char, that contains a single node containing the value A and that points to nowhere. We could also create a two-level tree of value 3 integer that has the root node of value 8 and points to two other nodes of value 3 and 10, and both of those point to empty trees, meaning they don't have any children. And we can keep building on top of that for a three-level tree of type integer that contains the node 8, that has two children, the node 3 and the node 10, and the node 3 has the children 1 and 6, and the node 10 has only the children of value 14, and it doesn't point to anywhere else. This value is almost the same, except for the last two children, as the value we had in the image before. Awesome! We have our data type ready to run. We now need to implement the function to check if an element is inside a tree. We start, as always, with the type. The function will take a value of type A and a tree of values of the same type. It will check if the value is inside the tree and return a bool of value true if it is and false if it isn't. So we can start with a type signature like this one. lm3 takes a value and a tree of values and returns boolean. Now, because the tree type has two constructors, we know that it's likely we'll need two definitions, one per constructor, as the two cases. One for when the tree is empty and one for when it's not. So we have this. If the tree is empty, the value we provided is obviously not inside the tree, so we return false. And what if the tree is not empty? Well, we just pattern match the node and we have its value right there. So you might as well check if that's the one we need. So if the value provided is equal to the value of the node, then we return true. The value is inside the tree. And because we are checking for equality, we know that A has to be an instance of the equality class. So we add the constraint to the signature. So if it's equal, we return true. End of story. But if it's not, we have to choose the subtree to keep looking. And that depends if the value is bigger or smaller than the one in the node. So we not only have to check if the value is equal, but also greater or smaller than the value of the node. Because now also we have to check for greater than and smaller than behaviors, the type A has to be an instance of the OR type class. And because, like we saw in previous lessons, to be an instance of the OR type class, you have to previously be an instance of the equality type class, we can remove that constraint and just put the OR constraint. Remember that you don't have to memorize all this. In the created type classes lesson, we will learn how to quickly check all this. We also will need a bunch of nested if-else statements, so we switch to guards for a more straightforward code. So we first check if the value is equal to the one in the node. In that case, we return true. If that is false, we have to check both if the value is bigger than x and if the value is smaller than x. And what do we do in these two final cases? Let's see. If the value provided is bigger than the value of the node, we know that if the value is inside the tree, it will be in the right branch, where all the values are bigger than the value of the current node. So the only thing we have to do is to recursively check the right subtree with the same initial value. And if the value is smaller than the value of the node, we know that if the value is inside the tree, it will be on the left branch. So the only thing we have to do is to recursively check the left subtree with the same initial value. And that's it. We have a way to check if a value is in our data type using the binary search algorithm. As you can see, we can apply lm3 to 6 and the 3-level tree we defined previously, and 6 was the second node, so it returns true. And we also apply lm3 to a number that is not inside the 3-level tree, and we get false, as expected. Remember that we are in an interview, and that's a great solution. The thing is, while you were thinking about this, you got so focused on your thoughts that you never noticed 15 minutes had passed without you saying a thing. The interviewer got a bit scared and told you that it was great meeting you and they will communicate to let you know if you passed the interview. So the takeaway is, in your next interview, remember to think out loud while working on problems. It helps the interviewer know your thought process, and you avoid showing the face you make when binge watching Haskell videos. Yes, the one you're making right now. But don't worry, you will have more hypothetical opportunities. For now, we'll still have a few more things to see today. For example, the fact that the shape of the data type directs how you write functions with it. Now, this is not written in stone, but in general, you have one equation per value constructor. And if a value constructor is recursive, 1 or n times, the equation will be recursive 1 or n times. For example, the box A data type has two constructors, the empty and has constructors, and none of them are recursive. So, when you write a function for this data type, it's likely you will need to write two formulas, meaning two definitions, one per constructor, and no formula will have a recursive call. The sequence data type has two constructors, the empty sequence and the weird arrow, and one of them, the weird arrow, is recursive because it has a value of type sequence A as a second parameter. So, when you write a function for this type, it's likely you will need to write two formulas, one per constructor, and the formula that matches for the weird arrow constructor will have a recursive call of the function you're defining. Finally, the tree data type has two constructors, empty tree and node. And one of the constructors, the node one, is 2 times recursive because it has two trees as parameters. So, when you write a function for this data type, it's likely you will need to write two formulas, one per constructor, and the formula that matches for the node constructor, we have two recursive calls of the function you're defining. Of course, there are cases when this rule of thumb doesn't apply, but you can use it to get started whenever you're unsure on how to define a function. As you can see, there's so much going on with types, value constructors, type constructors, etc., that it's hard to keep track of things. Thankfully, Haskell has a trick up its sleeves. Kinds. Let's go back to the simple days. Remember the box type? No? Let's see. It has a value constructor called has. Let's check its type. Okay, so has takes a value of type A and returns a value of type box A. Cool. And what's up with that box type? How can I know more about it? If you try to check the type of a type, you will get an error. Haskell will think that box is a value constructor and it will tell you that it's not in the scope. But box is not a value constructor, it's a type constructor. And there's a way to know more about type constructors. We can use the info command, and we will see in the second line is the definition of the box type. But what in the world are those stars in the first line? That's the box kind. Same as how the type of a value constructor gives you the quantity and type of value it takes. The kind of a type constructor gives you the quantity and kind of types it takes. Let me say that again. The type of a value constructor gives you the quantity and type of the values it takes. The kind of a type constructor gives you the quantity and kind of types it takes. So, a kind is like the type of a type. And you can read kinds like this. The single star means concrete type, a type that doesn't take any parameters, like float, int, double. Star to star means a type constructor that takes a single concrete type and returns another concrete type, like box A. And this huge thing means a type constructor that takes one concrete type and one single parameter type constructor and returns a concrete type. We haven't seen this yet, but we will in the more advanced lessons. So let's see a few examples. Int, string, and bool are all concrete types. They just have a single star that indicates that these types don't take any parameters. As you can see, you can also check the kind of a type by using the k or kind command in GHCI. Other examples are box, sequence, and tree that are type constructors with one concrete type as parameters. We can see that its kind says that it takes one concrete type and returns one concrete type. And another example is the entities type synonym that, as you can see here in the definition, its kind correctly says that it takes two concrete types and returns a concrete type. As you can see, type synonyms also have kinds because they can also have type parameters. Another thing, notice that as soon as a type constructor gets all its parameters, it becomes a concrete type. The kind of box is type to type, but the kind of box string is a concrete type because it doesn't take any more parameters. And you can also partially apply type constructors, the same as with functions or value constructors. So we have the data type double box with a type constructor that takes two types. So the kind of double box says that it takes two concrete types and returns a concrete type. The kind of double box string still says that it takes a concrete type to return a concrete type. So double box has been partially applied with a single type. And if we finish applying all the parameters, we of course get that double box string int is a concrete type. So next time you need to know a bit more about a type constructor, you can check its kind. And now, to finish the lecture, I'll give you one more teeny tiny piece of information. But don't worry, you don't have to learn anything more than a caveat and a single keyword. And that keyword is the newType keyword. newType works essentially the same as the data keyword, except for an important caveat. Types created with newType need to have exactly one constructor with exactly one parameter or field, like this. We have the color data type that has one constructor and one parameter. So we can use newType instead of the data keyword. We also have the product type that has one constructor, the product constructor, and has one single field. So instead of using data, we can use the newType keyword. But you can also do that with data. So why should we use newType? Short version, performance reasons made by the compiler. So if you happen to be creating a data type with one constructor and one parameter, you can switch the data keyword with the newType keyword and get a performance boost for free. And that's it for today. Remember to complete your homework, and I will see you in the next one.